Let us do another example. Do you have any questions before we start, by the way? Now you see, in the first example, we had these infinite planes connected by the edge. Now I will assume that I have two infinite strips, horizontal, and two vertical infinite strips. So it's like a cylinder, but the cross-section will be a rectangle, not a circle. So basically, this is what we will have. And of course, in both directions. And I will choose my x and y axis. And this is, let's say, A, this is B. And again, the upper plane and the lower plane, they will be both grounded. This side, let's say, will be at potential V0, Y. It doesn't depend on Z. And this side will be at a potential V1 of Y. Again, nothing depends on Z. So that we will be basically getting rid of one of the coordinates. I mean, you can generalize it to functions that contain the Z. Now we have these two plates, parallel, and two other parallel plates that are perpendicular to the first ones. So just imagine a rectangular prism, but goes to infinity. The height is infinite. Now, in this case, whatever we did in the previous case, we will do exactly the same thing, and we will obtain exactly the same x and y. So this will be our solution. Nothing changes up to this point. Again, we have the boundaries phi of x, y is equal to 0, is equal to phi of x, y is equal to, let me change a and b, y is equal to a. These should be 0 because the upper and the lower strips are at 0 potential. So this will again just tell me that delta k should be equal to 0 and k is equal to n pi over a. N being 1, 2, etc., positive integers. So phi n xy will be a n sine n pi over a y times bk e to power kx plus ck e to power minus kx. You see, in the previous case, x is equal to infinity was in our region where we are solving for the potential, but in this case we are solving for the potential in a region where x can take at most the value b. X takes values between 0 and b. So everything here is finite, and the potential is definitely not 0 when x should be equal to b. So this is what we can do at most. Well, I will also get rid of, no, this is not bx, let me also call them. This is bn, cn, n pi over ax, n pi over ax, which is sine of n pi over ay, bn times an, e to power n pi over ax, plus cn times an, e to power n pi over ax minus. So I don't really have 3 sets of unknown coefficients. I only have 2 sets of unknown coefficients that will determine my function, cn times an and bn times an. I can just give them some different names. Let me just call them, this is dn, this is en. So phi n, x, y is sine n pi over ay. times dn e to power n pi over ax plus en e to power minus n pi over ax. Now, this function satisfies the Laplace equation, or any superposition of these functions satisfy the Laplace equation. They satisfy the boundary condition at y is equal to 0. They satisfy the boundary condition at y is equal to a. Of course, just a single one of them does not satisfy the boundary conditions at x is equal to a and x is equal to b. But we can still take their superposition and the remaining boundary conditions we can impose on this function, and the remaining boundary conditions phi at x is equal to 0, y. This should be v0 of y. This is our boundary condition. But this is our general solution. So if you put x is equal to 0 over there, the general solution just becomes n sine n pi over a y times dn plus en. So in this case, dn plus en, these coefficients are the coefficients of the Fourier sine series of v0 of y. Of course, this is not enough to determine all dn and en, because this will only tell me what dn plus en is. If I want to determine dn and en, I need one more condition on them. But that is from the other boundary condition. When x is equal to b, remember I had this rectangular prism, y is equal to 0 was v0, and then x is equal to 0 was the potential v0, and x is equal to b was the potential v1. Sum over n sine n pi over a y times dn e to power n pi over ab plus en e to power n pi over ab minus. And again, now this combination of dn and en coefficients are the coefficients of Fourier sine expansion of v1. So now I have two conditions on, just take the Fourier sine expansion of these functions, find their coefficients. That will give you an equation on dn plus en and another equation on this combination. So you have two unknowns, you have two equations. You can determine the coefficients and you are done. Once you determine dn and en, you know the potential everywhere. Let's do a different example now. Now, what I would like to find is the potential inside a sphere but on the surface of the sphere, my potential is a function of theta on the surface. Well, let me also first define what theta is. These are my x, y, and z coordinates. And with these coordinate axes, the potential on the surface is a function of theta. It can be constant in certain regions, have a different value in other regions, etc. So this is what I want to determine. I can still use the separation of variables in Cartesian coordinates. There is nothing that prevents me from doing that. But the problem is, how do I impose the boundaries? You see, in the previous example, my boundaries were simple. One of the coordinates is equal to constant. That was my boundary. So that was kind of easy. Now here, if I use the Cartesian coordinates, the surface of the sphere, on the surface of the sphere, none of the single coordinate is 0. But some combination of them is constant. But if I use, for example, spherical coordinates, then my coordinates will be r, theta, and phi. Then I'm kind of done. Since the boundary is r is equal to constant, so it will be a simple condition that specifies my boundary. So that's why to solve such a problem, I would rather use the spherical coordinates, although I could have just as well used the Cartesian coordinates. In Cartesian coordinates, the solution will be very complicated. In spherical coordinates, at least the boundary is much simpler, the expression of the boundary, so I hope the solution will be simpler. Now, the second thing I observe, at least in this problem, since the potential on the boundary only depends on theta, nothing really depends on phi. If I rotate my system around the z-axis, nothing should change. Well, nothing changes, not my boundary, neither my equation. So my solution should also be independent of phi. Okay, so my potential will be a function of the coordinates r and theta only. It won't depend on the coordinate phi. So let's start with the Laplacian. Laplacian acting on a function that depends on only r and theta is, let's just check it up. So this is equal to 1 over r squared d by dr, r squared, the derivative of the function with respect to r, plus 1 over r squared sine theta, d by d theta, sine theta, derivative of this function with respect to theta. This is my Laplacian. I will just repeat the same steps as in Cartesian coordinates. What was the first thing we did? Our first assumption. Phi is a function of, is a product of functions of a single variable, single argument. So I know that my potential depends on r and theta. I'm just assuming that it is a product of a function that depends only on r and another function that depends only on theta. This is the symbol I use for that other function. I have a sphere. No, it's not cylinder. It's a sphere. Well, there are no charges inside. I mean, we didn't yet study what happened in material, in matter. It's empty inside, so the potential satisfies the Laplacian inside since there are no charges inside. And we know the value of the potential on the boundary, on the surface of this sphere. Either we measured it or we just connected our batteries so that we know the potential.
Hocam sadece ağırlık theta bizim boundary'yi belirtmemize yetecek mi? Yani oradan bir patch'i mesela yapılsak bir patch olsa payıyla belirlememiz gerekmiyor mu?
Well, you see, we are just kind of simplifying the problem. In general, your boundary, the value of your potential on the boundary will depend on phi. But just for simplicity, rather than dealing with three variables, I want to deal with two variables because the idea is basically the same. So for simplicity, I'm assuming that this is a special problem, not a general problem. This is a special case in which the value of my potential at the boundary depends only on theta. It doesn't depend on phi. Well, if there is a phi dependence on the boundary, of course, in that case, you have your potential will depend on r theta and also the phi coordinate. So you will assume that it's the product of three functions. not just 2.
But the techniques is the same.
Identical. The steps will be identical.
Hocam bu aynı tetanın arasındaki işaret ne işaret?
This one, this is capital theta.
Ne anlamda?
What should I call my function? Z of Zeynep. Okay. If you don't like capital theta, let me call it Z. Or ZE maybe.
Ha, aferin.
The name of my function.
Ben işareti mi diyorum, ne diyor?
It's the name of my function. Okay, let's put it now in our equation. So Laplacian acting on this potential will be, well, the first, here the derivatives only act on R. So they don't act on ZE. I can take it out. What remains is 1 over R squared d by dr, R squared dr by dr. Plus, here in the second term, the derivatives only act on ZE. They don't act on capital R. So I can take it out. 1 over R squared sine theta d by d theta sine theta d by d theta acting on ZE. I will again divide by R times ZE, both sides. Or I will divide by phi, which should be 0. This is equal to 1 over capital R, 1 over R squared d by dr, R squared dr by dr, plus 1 over R squared, 1 over ZE, 1 over sine theta, d by d theta, sine theta, dZe by d theta. Again, let's look at this equation. This equation should be always 0, whatever the value of small r or whatever the value of theta is. Keeping r constant, if r is constant, this is constant, this is constant, this is a function of theta. I can change theta, but if this equation is always equal to 0, whatever the value of theta is, so this combination shouldn't change as I change theta. It just tells me that this combination should be a constant. So 1 over ZE, 1 over sine theta, d by d theta, sine theta, dZe by d theta. This should be a constant. I will write it in this form. Now, why did I write it in this form? You will see in a moment. Just, you see, before we had these constants, I wrote those constants as the square root of a positive number. Now here we have another constant. I will write this constant in this form.
If R is not constant,
If,
R is changing.
well, you see, my solution should satisfy this equation everywhere inside my sphere, at every point. It should also satisfy this equation on a sphere inside my region. Well, on this sphere inside my region, R is constant. So I can keep in my region, I can keep R constant and look at points that differ by theta, by the theta coordinates, and for all of these points, that equation should be satisfied. Well, if I make that definition, then R satisfies this equation. this should be equal to 0. No, minus, because this ratio is minus L times L plus 1. Do you know how to solve this equation? Let me rewrite this. Let me multiply everywhere by this r squared, so I will get rid of that r squared. Let me multiply by r and take that derivative. So when I do that, that equation becomes r squared, the second derivative of the capital R, plus twice r, the first derivative of r, capital R, minus L plus 1 times r squared. This is equal to 0. Now, the special property of this differential equation is that you take the second derivative, multiply by the square. You take the first derivative, multiply by r. You take 0th derivative, you don't multiply by r. And in fact, an equation that has this form where when you take the nth derivative of your function and multiply by the argument to the power n, the solution is a simple polynomial. It's a simple power of r. So if you try, let's assume r is equal to its argument raised to the power n. Let me just look for such a solution. If you put it, the second derivative will bring a factor of n times n minus 1, r to the power n minus 2, but I'm multiplying with r squared, so r to the power n, plus 2n r to the power n, minus L plus 1, r to the power n should be equal to 0. R to the power n's I can cancel, n times n plus 1, minus L times L plus 1, this is equal to 0. Now this is basically why I assume this n I don't know, this is why I put this here, L times L plus 1. That funny combination. So n is equal to L, or n is equal to minus L plus 1.
These are all the higher terms. Can we deduce these?
Which higher terms? There are no higher terms. This is the solution that we are trying. I'm not ignoring other terms. This is the solution. Now, this kind of differential equation in which you multiply the nth derivative by the variable to the power n, their solutions are this form. They are not, I'm not talking about a series, just like single term.
Ben şey demeye çalışıyorum, böyle sadece önümüzdeki bu örneğe bakarak böyle bir generalization yapabilir miyiz?
Well, mathematicians do it. So, I mean, in fact, this is the basic idea. So, since you are taking the nth derivative, if you take the nth derivative, you are reducing the power by x to the power n. If you multiply it by x to the power n, the power doesn't change. So all terms will have the same exponent. They can cancel, you get the solutions. Now here I multiplied everything by r squared and capital R. Well, you see, I'm taking the derivative of this thing, r squared times the derivative of this one, that's the second derivative. The derivative of this one, which is 2r, multiplied by this term, the first derivative. And here there's no r squared, it's just r. And this r squared cancels this r, I'm left with capital R. So this is a second order differential equation. I have two solutions. That is the most general solution. L times r to the power L plus BL over 1 over r to the L plus 1. This is the solution of the radial part. Now comes the more complicated part. this one. Well, again, this is a second order differential equation, which in principle should have two different solutions. But you see, we have boundary conditions. Ze when theta is equal to 0, and Ze when theta is equal to pi over 2, should be finite. And we are not saying that they should have this value or that value, but they should be finite. Now, among the two solutions of this equation, there are two things. Among the two solutions, one of them is not finite. At theta is equal to 0 or theta is equal to pi. And such solutions exist that are finite at theta equal to 0 or theta is equal to L if L is a positive integer. L is an integer. That is one thing. L should be an integer, otherwise the solutions are not finite. Again, if you remember, in the previous case, we said that this n should be an integer because we want the solutions to be 0. In this case, we don't impose that condition, but we want finite potential. The potential cannot just go to infinity. It should be finite. And this condition tells me that that L over there should be an integer, not an arbitrary number. And next, the solutions are what are called the Legendre polynomials. Now, what are they? They are studied, tabulated, etc. Okay, P0 of x is equal to 1. P1 of x is equal to x. P2 of x is equal to 3x squared minus 1 over 2, etc. You can look at for their tables. For us, the important thing will be this. PL of x, PL of x prime, now PL prime of x. If we integrate them from minus 1 to 1, it's equal to Kronecker delta. So if you multiply two different ones and integrate them from minus 1 to 1, they give me 0. Or let me rewrite it in a different form. If we take PL of cosine theta, now that is what we will be interested in, PL prime of cosine theta multiplied with sine theta and integrate over theta from 0 to pi. This is equal to Kronecker delta LL prime. Minus 1 corresponds to cosine theta is equal to minus 1, so theta is equal to pi. The other one corresponds to theta is equal to 0.
Why did you write the extra sign theta?
Well, what I did to obtain this one from here is just made a change of variable. X is equal to cosine theta, so dx is equal to sine theta d theta. Okay, now the last question. What happened to the minus sign? If x is equal to cosine theta, dx is equal to minus sine theta d theta. I flip the limit. You see, the lower limit, when I make that change of variable, corresponds to pi, which is the upper limit over here. So if I just make the change of variable, there is a minus sign, but the limits are from pi to 0, not from 0 to pi. So I flip them, I get the limits from 0 to pi. Now these are the things that we will need only. Maybe from time to time we might use the explicit expression for a few of them, one or two, P0 or P1 that we might use, but most of the time that will be enough for us. We don't need to know the general expression, properties, etc. This is what we need. And PL is basically a polynomial of order L. And they are complete, meaning that if you have a function of theta, then we can write that function in terms of as a sum of PL cosine thetas. That's the completeness theorem. We are not going to prove that. We will just assume it that it is.
What is the special feature of Legendre polynomial?
They satisfy this equation, which is the equation we get when we try to solve Laplace equation in spherical coordinates. That's why it appears in many places and it's greatly studied.
Burada sadece şeye bağlı olduğu için, AGT'ye bağlı olduğu için değil mi? AGT fay olsaydı o zaman Legendre.
If you want to hear it, in that case, a side note, and they are called, again, the Legendre polynomials, but associated Legendre polynomials. I mean, just to tell you that they exist, but we will not be dealing with them. Anyway, let's come back to our solutions. Now we have our radial solution. We have the angular solution. So the solution we have for our function is AL times r to the power L plus BL 1 over r to the power L times PL of cosine theta. Well, this kind of satisfies all the boundary conditions that we have. Yeah, not satisfied, but it has the possibility of satisfying, let's say. Now, if you want to impose specific boundary conditions, then our potential, the general expression, will be just a summation over L from 0 to infinity of AL r to the L plus BL 1 over r to the L PL of cosine theta. Now, up to this point, the only condition I imposed on my solution is that the only conditions, it doesn't depend on phi. That's the assumption, one of the assumptions I started with. And secondly, it is finite everywhere. So that the theta solution, the equation for theta, of course, it has two different solutions, but one of them is not finite, so we throw it away. And secondly, if I want the solution to be finite everywhere, including theta is equal to n pi, L should be integer. Now let's come to our question. What was our question? We had this sphere on the boundary. We had the value was v of theta on the boundary of the potential, and we are looking for the potential inside. This is the general solution, whatever the boundary value is. No, not phi L, this is phi. But you see, in this region, inside my sphere, there is the point r is equal to 0. My potential should be finite at the point r is equal to 0. Now this is L plus 1, sorry. My solution should be finite at r is equal to 0, but this term diverges at r is equal to 0 for all values of L. So since my solution is finite at r is equal to 0, this term shouldn't appear. But you see, the solutions of the Laplacian, I'm looking for the solutions of the Laplacian. If I have, let's say, 1 over r over there, if it gives me Dirac delta, that's not nice. I wouldn't like to have them. Or I also know that since I know the value of my potential and the boundary to be finite, no charges are inside, so there cannot be any maximum inside. Infinite is definitely a maximum. So I know my phi. This is my solution inside. I still don't know what ALs are. But again, I didn't impose any boundary conditions yet, except that the potential should be finite. Now I can impose my boundary condition. On the boundary, whatever the value of theta is, I know that phi is a function. This is a known function that is given to me. And this should be written as LE from 0 to infinity, a L r to the power L PL of cosine theta. Now I need to extract this AL. And to do that, I multiply by sine theta PL prime cosine theta and integrate over theta from 0 to pi. So that gives me V theta, sine theta, PL prime cosine theta, d theta, from 0 to pi. This should be equal to, L is equal to 0 to infinity AL, R to the L, PL cosine theta, PL prime cosine theta, sine theta, d theta from 0 to pi. But the definition of the Legendre polynomial, sorry, I forgot. Okay, this is not Kronecker delta, but 2 over pi over L plus 1. 2L plus 1. 2 over 2L plus 1. This integral from the definition of the Legendre polynomials is 2 over 2L plus 1 Kronecker delta LL prime. Now I can sum over L using that Kronecker delta, because Kronecker delta tells me that in this infinite sum over L, only the term L is equal to L prime gives a contribution, and that term is AL prime RL prime 2 over 2L prime plus 1. So if I know the boundary condition, I know what AL primes are. And once I know what AL primes are, I know my potential. We could have just as well looked for in this problem, we could have just said, okay, I have my sphere. On the surface of my sphere, the potential is given by V theta, whatever that function is. What is the potential outside? I could have also asked that. The only difference in that case would have been, you see, outside, I don't have the r equal to 0 region. R equal to 0 point is not in the region that I'm trying to solve my Laplace equation. So this term is no problem. But this time, this term would have been a problem because outside my sphere, there is the r is equal to infinity point. And my potential should be finite. But this term diverges. And my potential should go to 0 at infinity. This term diverges if L is non-zero. If L is 0, this term is constant, but that constant should go to 0. So that term AL should be 0 in that case. I only have this one. Again, how do I determine B's? Well, I just said small r is equal to capital R, which is my boundary. Find the expansion of V of theta in terms of PL. And again, I'm done.
Is it r to the L plus 1?
R to the L plus 1. Well, let's do a simple example. A very simple one. We already know the solution of a sphere that has a constant potential. That's a conductor. if the surface of the sphere is a constant, v of theta is equal to v0, which is constant. Let's look at that integral from 0 to infinity, v of theta, sine theta, PL prime cosine theta, d theta. Well, this is v0, that is v theta. Inside I have sine theta, PL prime times cosine theta, integrate over theta. There is a 1 over here, 1 is multiplied by 1, but 1 is P0. P0 is just 1. So that product, that integral, and we already know the result, it is 2 over 2L prime plus 1 Kronecker delta L prime 0. 2V0 Kronecker delta L prime 0. So in this summation, if we have a equipotential sphere, in this summation, only the L equal to 0 term survives. L is equal to 0 term is just a constant. So we already know that in a conductor, inside is a constant potential. Okay, any questions? So your homework is for Tuesday. You will get your new homework also on Tuesday. The exam is next weekend on Saturday downstairs.